Having talked about how stars can be classified, how they form, and how they evolve, we should now look at sort of the byproducts or the trash that they somehow leave behind that is so important for us to exist. And these are planetary systems that form while many stars form, essentially from the leftovers. And in section 10, we're going to focus on our own solar system, including our own star. These are the topics that we'll be covering to do with our own solar system, how it forms, some further details about the sun and the interaction of the sun with our planet. We'll define what a planet is and what is a dwarf planet. We'll roughly discuss the big difference between the terrestrial planets and the gaseous planets. And we'll discuss a little bit about the full extent of the solar system and whether there is a planet 9. And as always, you'll find even further information, details, and discussion in your lecture notes for section 10. In an ideal world, we would just get a time machine and then go back in time billions of years until the time where the solar system was in formation. And if we were able to do that, it would probably resemble something like this, where the disk was still around and the planets were still growing as they orbit the disk and essentially clear it out. However, we can't really go back in time to our own solar system, but what we can do is use the tools of sort of archaeology to look at the end product to try to unveil what kind of conditions existed when the solar system started forming. There are several things that we can observe from our solar system right now, essentially clues as to how it formed. For example, we know that all planets, and I'll come back to this, what a planet is and why Pluto is no longer a planet, all planets essentially lie in the same plane within 3.5 degrees. This is probably an indication that they were all formed in a disk. On the other hand, most orbits are really circular. The eccentricity is below 0.1. Notable exceptions for things that go around the sun include Pluto, which is not a planet, but a dwarf planet. This was already evidence that it was different, but one of the planets actually has a high eccentricity, and that is Mercury. We also know that all planets go around the sun in the same direction. And we also know that the sun is essentially rotating at an inclination that matches the one that the planets are rotating around, which is further evidence that everything formed from a disk. There are also some extra interesting observations of the different planets and how they're rotating. For example, Earth, Saturn, and Neptune are actually tilted. The Earth is tilted by something like 23.5 degrees. Saturn is tilted 26.7 degrees in terms of the plane that captures all the planets. And Neptune is tilted by 29.6 degrees. Venus, for example, is even weirder because it actually rotates the other way around, although very slowly. It's almost as if it doesn't rotate. And Uranus is also kind of weird because the rotation axis is approximately in the plane of the orbit. And all these are probably indications that while all the planets formed in the disk, they probably encountered a lot of collisions, because through collisions, you can actually tilt the rotation axis or even reverse the rotation like Venus. Something else that we can have a look at in terms of the planets is their size distribution and also what they're made of. For example, the inner planets are all rocky. This includes Mercury, Venus, Earth, and Mars. While the remaining planets, the outer planets, are all gas giants. They're much larger and way less dense than the rocky planets. We can also see that roughly planetary size is increasing, essentially as we move away from the sun, perhaps with the exception of Mars. But once we get to Jupiter and Saturn, it then decreases again. And this may be telling us about the conditions in the disk when these planets formed. By making observations of the solar system right now, we can actually infer a lot about the origin of the solar system, or what was there in the pre-solar nebula. We know that because of what makes the planets and the sun itself, that this pre-solar nebula contained mostly hydrogen and helium, but it also had to contain all the other elements that are present in the planets, such like the Earth. And we know that the total mass had to be a few times the current mass of the sun. Given the amount of heavy elements that we can see in the atmosphere of the sun and also in planets like the Earth, we know that the material had to result from supernova explosions, and that the star is actually what we would class at least a third generation star. Essentially, the materials have come out from at least kind of 3 generations of supernova explosions. We also know that the density of the pre-solar nebula had to be something around 10 to the 7 atoms per cubic meter. And this is much denser than the typical conditions of interstellar space, around 2 orders of magnitude higher. But if you compare it with the density of the atoms in your own room, where you're probably watching this video, we're talking about something that's way, way less dense. Just before the collapse, this pre-solar nebula probably extended tens of light years across, so way, way larger than the scale of the solar system right now, and it was probably very cold, around something like 10 Kelvin. In section 9, we already discussed the Viral theorem and how if you break the Viral theorem and gravitational potential energy is higher than the kinetic energy, or more specifically, if the gravitational potential energy divided by 2 is higher than the kinetic energy, then you have the conditions for a spherical cloud to collapse. And we expect that this was definitely the case for the pre-solar nebula. We derived an expression for the Jeans mass, and this is just another example. You can also write it in terms of the initial density, and we've seen how this depends on the temperature. This is the actual expression that we derived. It will depend on the material that the pre-solar nebula was made of, the temperature, and also the radius, and this is just another way of writing it. Of course, because the sun formed and we are here, we know that this condition actually happened, and by using different forms of the Jeans mass and actually looking at the solar system right now, we can try to infer some of its initial parameters. In general, when a cloud breaks the Viral theorem and it starts to collapse, a lot of things happen that lead to other physical consequences. For example, once contraction starts, you expect heating to go up and temperature to go up. You also expect the pressure to go up, and the density is also rising as your cloud is collapsing. As the cloud collapses from sizes of a few light years or something like 60,000 AU to a ball that's more of the size of the full solar system right now, we expect temperatures to go from the initial 10 K to something like 1000 Kelvin. And because of conservation of angular momentum, you actually expect rotation time to decrease from something like several millions of years to days, meaning all things in the cloud are now moving way, way faster. As a consequence of the collapse and the rotation becoming faster and faster due to conservation of angular momentum and the radius becoming smaller, you actually expect the spherical object to start having flattening poles. On the other hand, centrifugal forces will be really large at the equator compared to the poles, meaning that the cloud will start to have a much more lenticular shape and actually becoming more and more of a disk, like you can see here. At the center of the disk, this is where it's dense enough that you start to form a spherical object that continues to shrink under its own gravity. This is where the temperature and the density will be the highest. And at some point, and certainly for the sun, this was the case, the core becomes hot enough, around 15 million Kelvin, for nuclear fusion to actually kickstart. And at that point, the star is actually born. As fusion starts, then there's actually counterbalancing force of radiation pressure pushing back. And at this time, the star becomes a main sequence star, but still surrounded by a protoplanetary disk that has not been cleared out yet. We will not be looking at all the quantitative details. We've seen how we can actually calculate the Jeans mass. This is the condition necessary for the cloud to collapse. And I've given you some qualitative arguments of why this cloud will eventually form a disk due to conservation of angular momentum and the forces on the equator becoming stronger than in the poles, leading to a lenticular shape. And then as the cloud becomes smaller and smaller, rotation actually peaks up, leading to a disk. And at the center, this is where you form the protostar and then the star itself. But even after the sun is born, the disk will still remain, and we expect accretion to lead to these planetesimals and then ultimately to planets being formed. But one of the things we can try to address is, why are planets so different if they all formed out of the same disk? Can we use simple physics to actually explain their positions, their masses, and composition? In terms of explaining how planets form, there's perhaps two very important aspects. One has to do with how much material there is to accrete. And if you're actually in a wider orbit, you will be essentially gathering more material than if you're in a smaller orbit. But perhaps more important is to understand the balance between the escape velocity of a given element that perhaps you're trying to accrete, but also the typical velocity or the RMS velocity of that material within the disk. Why is this important? It is important because essentially the velocity at which specific hydrogen atom or an helium atom will be moving will depend on the temperature. And this means that if you're trying to accrete hydrogen from very close to the sun, because the temperature is very high, this typical velocity will be very high. So the only way you can hold on to it, because of the way that you can calculate the escape velocity, is if you actually had a big mass. But very close to the sun is actually very hard to accumulate that mass. As a consequence, what happens is that dense cores far from the sun can actually accrete gas to form planets like Jupiter. And this is simply because the typical thermal velocities away from the sun are much lower and they are below the escape velocities. And therefore, planets like Jupiter and Saturn can very easily grow and they can hold on to, say, hydrogen and helium. However, if you're trying to form a gas giant close to the sun, you simply cannot do that because every time you try to hold on to hydrogen, then it will just go away because its typical RMS velocity is higher than the escape velocity. If we compare the typical escape velocity with the typical velocities in terms of a distance from the sun, we can actually very easily explain why planets forming very close to the sun are all rocky and planets further away from the sun are gaseous. This is because the inner disk regions are essentially too hot for most material to condense into larger aggregates of particles. We can explain why Mercury is the first planet, because around there is where metals can just begin to aggregate together. Essentially, if you're trying to form something even closer, that is simply not possible. And also from simple physics, we can understand why the gas giants also have a rocky core, but they're actually able to hold on to gases, while terrestrial planets simply were not, because the typical velocities were too high and in excess of the escape velocity. Now, on top of temperature being crucial in terms of your capability to actually keep some of the light elements, the planetary size can also be described essentially by the orbit circumference. Essentially, if you're forming further away from the sun, you should be able to sweep more material. And in general, this sort of explains why when we go from Mercury to at least Jupiter, the typical planetary sizes are going up. But then what actually happens is when we go further than Jupiter, the sizes go down. The reason for this is that even though in principle, the quantity of material that is swept up by planets like these should be higher, we understand that the disk itself had less material towards the outskirts than it had towards the center. So in a way, there is this sort of sweet spot around Jupiter where it's very easy to hold on to light elements like hydrogen and helium, and where you're actually sweeping up a lot of material and where the disk is still significantly dense.